There is a place in the universe so empty that if you could somehow stand at its center and look in any direction, you would not see a single star, no glowing galaxies, no distant shimmer of cosmic light, just blackness stretching farther than the human mind can comfortably process. Imagine taking every star in the Milky Way, every sun that has ever risen on Earth, every constellation you have ever seen, and placing all of it inside this region. Even then, the darkness would swallow it whole. The scale of that emptiness is not poetic exaggeration. It is measurable, it is mapped, and it exists right now, somewhere beyond the edge of our night sky, beyond the reach of backyard telescopes, and even beyond what most people imagine when they think of deep space. There are regions that challenge not only our understanding of astronomy, but our emotional ability to comprehend reality itself. Tonight, we are not exploring beautiful nebulae or gentle starlight. We are visiting the most terrifying places in the universe. Places so extreme, so vast, so violent that they almost feel fictional. Yet every one of them is supported by data collected by NASA, by radio telescopes, by space observatories, and by decades of astrophysical research. If you are watching from New York, California, Texas, Florida, or anywhere in between, understand this: the peaceful sky above your home hides realities far stranger and far more dangerous than anything on Earth. A void that should not exist. A star where metal falls like rain. A gravitational anomaly pulling entire clusters of galaxies toward a hidden destination. These are not science fiction concepts. They are coordinates in the cosmic map. And tonight, we begin with the silence that nearly breaks cosmology itself. Before we continue deeper, if this kind of exploration moves you, if you feel that pull toward the unknown, take a moment to like the video and subscribe. It truly helps the channel reach others who are fascinated by space, astronomy, and the mysteries of the cosmos. And I want to know something: what part of the United States are you watching from? Drop a comment and tell us your state or city. Are you under the clear skies of Arizona, the forests of Oregon, the skyscrapers of Chicago, the beaches of Florida? Let's see how far this community of explorers stretches across the country. Now, prepare yourself. Chapter 1 begins in the emptiest place we have ever found. In 2004, astronomers analyzing data from large-scale galaxy surveys identified something extraordinary. In the direction of the constellation Eridanus, they discovered a region of space so underpopulated with galaxies that it defied statistical expectations. This region, later associated with what many call the Boötes Void, spans roughly 330 million light-years across. To understand how incomprehensibly large that is, consider this: our entire Milky Way galaxy is about 100,000 light-years wide. You could line up more than 3,000 Milky Ways side by side and still not fill this void. Inside it, galaxies are astonishingly sparse. If you were located within this region, the night sky would not resemble the brilliant starfield we see from Earth. It would be profoundly dark, with vast stretches of nothingness in every direction. In cosmology, structure forms through gravity. After the Big Bang, tiny fluctuations in density allowed matter to clump together, eventually forming stars, galaxies, and the enormous filamentary structures known as the cosmic web. On the largest scales, the universe resembles a three-dimensional network of filaments and clusters separated by voids. These voids are expected. They are natural consequences of gravitational evolution. But the scale of certain voids has forced scientists to ask deeper questions. How did such a vast region end up so empty? Simulations of cosmic structure formation predict voids, yes. But when one grows this large, it challenges the statistical models used to describe the early universe. To appreciate the terror of a cosmic void, we need to understand what empty really means in space. Even the emptiest laboratory vacuum on Earth contains trillions of particles per cubic meter. Interstellar space within our galaxy contains perhaps 1 atom per cubic centimeter. But cosmic voids drop even lower, approaching densities so faint that matter is nearly non-existent. This is not just darkness, it is near absolute isolation. Light from distant galaxies must travel hundreds of millions of years just to reach its edges. If humanity somehow drifted into such a region, cut off from galactic clusters, we would lose visual confirmation that the universe beyond our local group even exists. From an educational standpoint, voids are crucial tools for understanding cosmology. Their size distribution helps scientists refine measurements of dark energy, the mysterious force driving the accelerated expansion of the universe. Observations of void shapes can reveal how gravity behaves over enormous distances. Some researchers even study the way cosmic microwave background radiation interacts with large voids, potentially creating cold spots in the ancient afterglow of the Big Bang. In fact, one unusually cold region in the cosmic microwave background has been linked by some to a massive void along our line of sight. While the debate continues, the mere possibility shows how emptiness itself can influence observable physics. Now imagine standing inside that emptiness, not metaphorically, physically. Suppose we had a spacecraft capable of traveling millions of light years. As we approached the center of such a void, galaxies would thin out. The luminous filaments of the cosmic web would fade behind us. The sky would darken not because night has fallen, but because there are simply fewer stars to shine. Our instruments would confirm it. Gravitational pull from surrounding matter would be weaker. The density of intergalactic gas would drop. We would be suspended in a cosmic desert stretching hundreds of millions of light years. Why is this terrifying? Because structure gives us comfort. Even subconsciously, we find reassurance in pattern and clustering in light. A void represents the opposite. It is the absence of formation. It is what the universe looks like when gravity has failed to build anything substantial. And in that sense, it reminds us that most of the universe is not stars and galaxies. It is space. Vast, expanding, and indifferent. Yet emptiness is only one flavor of cosmic terror. In another corner of the universe, there exists a place defined not by absence but by extremity. Picture a star larger than our sun, burning at temperatures so intense that atoms behave in ways almost impossible to imagine. On Earth, iron is forged in the hearts of dying stars and scattered across space in supernova explosions. It is heavy, it sinks, it forms planetary cores. But there are worlds where iron does not sit quietly underground. There are exoplanets so hot that iron vaporizes into clouds, condenses, and falls as rain. One of the most famous examples is an ultra-hot gas giant located hundreds of light years away. On this world, daytime temperatures exceed 4,000 degrees Fahrenheit. The heat is so extreme that metal atoms are stripped from their molecular bonds. Iron becomes vapor in the upper atmosphere. Powerful winds, driven by the temperature difference between the planet's star-facing side and its night side, carry this vapor across the globe. When it reaches cooler regions, it condenses and falls, literally raining molten iron. The science behind this phenomenon is rooted in thermodynamics and atmospheric dynamics. Exoplanets orbiting extremely close to their host stars are often tidally locked, meaning one side always faces the star while the other remains in perpetual darkness. This creates temperature gradients thousands of degrees wide. Such gradients drive supersonic winds, redistributing heat and atmospheric material. Spectroscopic observations allow astronomers to detect specific elements in these atmospheres by analyzing how starlight filters through them during planetary transits. When iron absorption lines appear and disappear in patterns consistent with atmospheric circulation, we gain evidence of metallic weather systems. Consider what this means from a planetary science perspective. Earth's water cycle shapes climate geology and life itself. On these ultra-hot exoplanets, there is a metal cycle. Iron evaporates, travels, and precipitates. The sky would not be blue. It would glow with incandescent heat. Lightning storms may crackle through metallic clouds. The surface, if one exists beneath the gas layers, would be unrecognizable. Such environments push the boundaries of atmospheric chemistry and fluid dynamics, helping scientists refine models of planetary formation and heat transfer. But terror escalates further when we move from stars and planets to the gravitational monsters lurking at the centers of galaxies. Nearly every large galaxy hosts a supermassive black hole at its core. Our own Milky Way contains one known as Sagittarius A, with a mass about 4 million times that of our Sun. That alone is staggering. Yet elsewhere in the universe, there are black holes billions of times more massive than our Sun. A supermassive black hole exerts gravitational influence over vast regions of space. Matter spiraling toward it forms an accretion disk, heating to millions of degrees and emitting intense radiation. Some launch relativistic jets that extend thousands of light years into intergalactic space. These jets can regulate star formation within entire galaxies, shaping their evolution. The physics governing these systems blends general relativity, plasma physics, and high-energy astrophysics. Imagine approaching one. From a safe distance, it might appear as a bright galactic nucleus, blazing with X-rays and ultraviolet radiation. As you draw closer, stars orbit at incredible speeds, whipped around by gravity. Tidal forces grow stronger. The event horizon, the boundary beyond which nothing can escape, marks the ultimate point of no return. Cross it, and all paths in space-time curve inward. Not even light can reverse course. Educationally, black holes provide laboratories for testing Einstein's theory of general relativity under extreme conditions. Observations from the Event Horizon Telescope have allowed humanity to image the shadow of a black hole for the first time, confirming predictions made over a century ago. Gravitational waves detected by observatories like LIGO reveal collisions between black holes, sending ripples through spacetime itself. These discoveries deepen our understanding of gravity, matter, and the fundamental structure of the cosmos. Yet beyond individual objects lies something even more unsettling: motion on the largest scales imaginable. In the 1970s, astronomers studying galaxy velocities discovered that our Milky Way and countless neighboring galaxies are not simply expanding away from each other due to cosmic expansion. Instead, they are drifting toward a specific region of space. This mysterious gravitational pull was named the Great Attractor. It lies hundreds of millions of light years away, hidden behind the dense plane of our own galaxy, making direct observation difficult. The Great Attractor is not a single object but a massive concentration of matter, possibly associated with enormous galaxy clusters. Its gravitational influence affects the motion of millions of galaxies across a region spanning hundreds of millions of light years. The existence of such large-scale flows reveals that cosmic structure is far from uniform. Matter clumps on scales so vast that they alter the motion of entire galactic populations. From an educational standpoint, studying these flows helps refine our understanding of dark matter distribution. Because visible matter alone cannot account for observed gravitational effects, dark matter must contribute significantly to these massive structures. By mapping galaxy velocities, astronomers infer the underlying mass distribution of the universe, including invisible components. Now imagine the psychological weight of knowing that our galaxy is in motion toward something we cannot directly see, not tomorrow, not in a human lifetime, but over cosmic timescales, drawn by gravity toward a distant mass concentration. It reminds us that even galaxies are not stationary islands. They are participants in larger gravitational currents. If one introduced us to the terror of emptiness and gravity, two takes us somewhere even more unsettling. Places where time bends, where radiation strips atoms apart, and where structures exist on scales so immense they force cosmologists to reconsider the limits of the observable universe. These are not simply distant curiosities. They are laboratories of extremity, regions that test the laws of physics at their breaking point. And in doing so, they reveal something deeply uncomfortable. The universe is not merely vast. It is violent, unstable, and often hostile in ways that challenge our deepest assumptions about safety and permanence. Let us begin near one of the most dangerous boundaries in all of astrophysics, the event horizon of a rotating black hole. In Chapter 1, we spoke of supermassive black holes in general terms. Now, we move closer, specifically to a type known as a Kerr black hole, one that spins at incredible speed. Unlike a non-rotating black hole, a spinning one drags spacetime itself around with it in a phenomenon called frame dragging. This effect is predicted by Einstein's general theory of relativity and has been experimentally confirmed around Earth on a tiny scale. But near a rapidly rotating black hole, frame dragging becomes extreme. Imagine approaching such an object in a theoretical spacecraft. As you near the black hole, spacetime does not simply curve, it twists. The region outside the event horizon contains an area called the ergosphere. Inside the ergosphere, spacetime is dragged faster than the speed of light relative to distant observers. Nothing, not even light, can remain stationary there. Everything is compelled to rotate with the black hole, in theory. Energy can be extracted from this region through a process known as the Penrose process, where particles enter the ergosphere and emerge with greater energy than they entered, effectively stealing rotational energy from the black hole. From an educational standpoint, this is profound. It demonstrates that black holes are not merely cosmic vacuum cleaners, they are dynamic engines capable of powering some of the most energetic phenomena in the universe. The relativistic jets emitted by active galactic nuclei are believed to be fueled in part by rotational energy extracted from spinning black holes. These jets can extend for thousands of light years, emitting radiation across the electromagnetic spectrum. But the terror lies in the physics of proximity. As you approach the event horizon, tidal forces increase dramatically. This is sometimes described as spaghettification. Gravity at your feet would be significantly stronger than at your head, stretching you vertically while compressing you horizontally. For smaller black holes, this effect would occur well before you crossed the event horizon. For supermassive ones, you might pass the event horizon before tidal forces become lethal, only to be inevitably crushed deeper within. And here lies the deeper horror. Once inside the event horizon, all paths in spacetime lead to the singularity. According to classical general relativity, the singularity is a point of infinite density where known physics breaks down. We do not yet possess a complete theory of quantum gravity to describe what truly happens there. This is not just a dangerous place, it is a region where our equations fail, a place where the known universe ends not spatially, but mathematically. Yet black holes are not the only regions where time behaves strangely. Consider neutron stars, the collapsed cores of massive stars that exploded in supernovae. These objects pack more mass than our sun into a sphere roughly the size of a city. A teaspoon of neutron star material would weigh billions of tons on Earth. The density is so extreme that protons and electrons are crushed together to form neutrons, creating matter in a state that cannot exist naturally anywhere else. Among neutron stars, there exists a subclass known as magnetars. These are neutron stars with magnetic fields trillions of times stronger than Earth's. To grasp this, understand that Earth's magnetic field protects us from solar radiation. A magnetar's field is so intense that if one were located halfway between Earth and the Moon, it could strip data from every credit card on the planet. Closer still, it would distort the electron clouds of atoms in your body, effectively pulling matter apart at the molecular level. Magnetars occasionally undergo starquakes, violent crustal shifts that release enormous bursts of gamma radiation. In 2004, a flare from a magnetar located about 50,000 light-years away briefly altered Earth's ionosphere. Despite that vast distance, the energy release was so immense that it affected our planet's upper atmosphere. Now imagine being within a few million miles of such an event. The radiation would sterilize any nearby system. Planets would be bathed in lethal gamma rays. Atmospheres could be stripped. Biological molecules would be torn apart. Educationally, magnetars help astrophysicists understand matter under extreme magnetic pressure. They serve as natural laboratories for quantum electrodynamics, the theory describing how light and matter interact. In magnetic fields this strong, even the vacuum of space behaves differently, exhibiting effects such as vacuum birefringence, where light polarization shifts due to intense fields. These are phenomena that push our theoretical frameworks to their limits. Now let us shift scale once more, this time not to density but to size. In 2013, astronomers reported the discovery of one of the largest known structures in the universe, a massive quasar group stretching approximately 4 billion light-years across. To contextualize this, the observable universe is about 93 billion light-years in diameter. The cosmological principle, the assumption that on large scales the universe is homogeneous and isotropic, suggests that structures should not exceed a certain maximum size before uniformity takes over. Yet this structure appears to challenge that expectation. If confirmed and fully understood, such enormous formations force cosmologists to reconsider how matter clumped together in the early universe. They test the limits of inflationary theory, which describes the rapid expansion of space fractions of a second after the Big Bang. Inflation predicts a smoothing effect, erasing large-scale irregularities. But when we observe structures of such magnitude, we must refine our models to explain how they formed without violating observed uniformity in the cosmic microwave background. From a human perspective, the terror is existential. These structures are so vast that light itself takes billions of years to traverse them. If you attempted to cross one at the speed of light, you would still not reach the other side in less than the age of Earth. They dwarf superclusters, galaxies, and any familiar astronomical reference point. They are cosmic continents in an ocean of space, and yet there is something even more unsettling than size or radiation or gravity. It is the concept of false vacuum decay. This is not an observed phenomenon, but it is a theoretical possibility grounded in quantum field theory. According to our best understanding, the vacuum of space is not truly empty. It is filled with quantum fields in their lowest energy states. However, it is possible that our universe exists in a metastable state, a local minimum of energy rather than the absolute lowest possible state. If that is true, then somewhere in the universe, a quantum fluctuation could trigger a transition to a lower energy vacuum state. This event would create a bubble of true vacuum expanding outward at the speed of light. Inside that bubble, the fundamental constants of physics could change. The masses of particles, the strengths of forces, even the structure of atoms might be altered. Chemistry, as we know it, would cease to function. Matter might not hold together, and because the bubble would expand at light speed, we would never see it coming. There would be no warning, no signal, just an instantaneous rewriting of physical law. This is not science fiction. It is a mathematically consistent outcome within certain models of particle physics. While current data suggests that such a decay is extraordinarily unlikely in the near future, the mere fact that it is possible highlights how fragile our cosmic stability might be. Consider what that means. The laws of physics, the constants that allow stars to shine, planets to orbit, and life to evolve, may not be absolutely permanent. They could represent a temporary arrangement in a broader landscape of possibilities. The most terrifying place in the universe might not be a location at all, but a condition waiting to emerge. As we reflect on, terror came from scale and gravitational pull. Here, it comes from extremity and instability. Black holes twist spacetime into spirals. Magnetars unleash radiation capable of sterilizing entire systems. Gigantic structures stretch across billions of light years, challenging theoretical limits. And vacuum decay suggests that even the rules of existence may not be eternal. Yet within this terror lies knowledge. Every one of these phenomena teaches us something profound about physics. Black holes confirm relativity and reveal gravitational wave mechanics. Magnetars test quantum electrodynamics. Large-scale structures refine cosmological models. Even false vacuum decay arises from precise equations in particle theory. The universe is terrifying not because it is chaotic without reason, but because it operates with laws so powerful and so indifferent that they produce extremes beyond our imagination. And as we continue into the next chapter, we will explore the final category of cosmic terror, not just physical danger, but temporal fate, the death of stars, the evaporation of black holes, the slow fading of light itself. Because the most unsettling realization of all may not be where the universe is dangerous, but where it is heading. If science and the vastness of space captivate you, then your place is right here. Subscribe to The Boring Universe and come closer to the cosmos with every new video.